Okay.
Hi, everyone. Thanks for joining us this week on the GeoScience and GeoEnergy webinar. It's 25th of February, 2021. And my name is Maren Bremer. I'm replacing Hadi again today because he has teaching duties. It's my pleasure to host you all together with Sebastian, as every week from Heriot-Watt. We are especially grateful to our keynote lecturers from our former presentations and for you for joining us this week from home. Please also subscribe to our YouTube channel, that allows you to see the upcoming talks. And our students, we still recommend to join the Forest Media Tea Time talks. There you can share your research and broaden your network. So now to the lecture of today. We are very pleased to have you, Pacelli. This week, we host Professor Dr. Pacelli Zitha. He's a professor and chair of GeoEnergy Production Systems and the director of the GeoScience and Engineering Laboratory at TU Delft. And he is doing research in fluid flow and porous media, polymers, foam, and magnetic fluids for 25 years now. Quite a long time, with mainly applications in improved and enhanced oil recovery. But recently, he's also doing research in geothermal reservoir engineering. From 2002 to 2007, he was the scientific director of the Deeds Laboratory at the Department of Mining and Petroleum Engineering. And before that, he worked as senior research advisor with Shell for 4 years. Pacelli holds a master's degree in theoretical fluid physics from 1991 and a PhD degree on condensed matter physics from 2004 from the University Pierre Marie Curie in Paris. It's our pleasure and honor to host you, Pacelli, in our Geoscience and GeoEnergy webinar this week. To the audience, as always, his lecture will last for about 30 minutes and will be followed by questions and discussions. Please type your questions in the chat and Sebastian will go through them after the talk. Pacelli, thanks once more again. The stage is yours. We're looking forward to your talk.
Thank you very much, Maren and Sebastian, for hosting me today for this talk. I'm very grateful for the opportunity to speak at this now premier platform for exchange, for scientific exchange. Today I will talk to you about well, a topic that might seem a little bit exotic for many people, how to store energy into the subsurface using electromagnetic heating. You might be wondering why one would want to do so. This talk is actually based on a very extensive cooperation that I've had in the last so many years with Gregory Shapiro from the Universidade Federal de Juiz de Fora, and also with his students and colleagues. I would like to acknowledge also other people that have shaped actually the thoughts that we have at the present about the topic. So now here you see a few names. On top, first you have people that used to be MSc students at TU Delft. They are, each one of them a very successful professional in the industry. We have Michiel Slob and Carol Heller, who are senior technicians. They're instrumental in all the experiments that I'm going to show. We have Professor Slob, Evert Slob, who is actually the expert in electromagnetic wave propagation methods, among other things. And then you see Gregory Shapiro and Pavel Pash. There are other people that I could mention, but well, these are the people at least that illustrate the whole lot. Now, to the topic itself. So in the last decade, there has been quite a bit of interest in methods for injecting energy into the subsurface and to a wide variety of ends. So, for instance, between 2011 and 2014, Chevron, multinational, for those who don't know, multinational oil and gas company from the US, conducted a steam drive demonstration project in one of its oil fields located at Coalinga, California. Now, this oil field bears crude oil, which is heavy crude oil, with API gravity of 12, density of 973, and a viscosity of 3,000 centipoise. It's important to mention this because that explains that this heavy oil cannot be recovered by other means than injecting heat into the reservoir to reduce the viscosity of the oil. And so in the schematic that I'm not going to go through the schematic in detail, I just want to point out one interesting feature of this project is that actually this project used solar energy. So we are talking about 2011, which means that all the study started even before that. But it used solar energy to generate steam, and then steam is injected into the reservoir, and steam will, of course, heat up the reservoir, reduce oil viscosity. It will partially condense, and then we will displace the oil with reduced viscosity to the production well, and that leads to substantial increase in oil production. And the oil is then separated. The water is recycled. That's always very useful to limit the usage of water. And then on the what you see here is a tower. Here you have so for concentrated solar power. Here you see the panels, one of the panels, and here you see the array of panels installed on the ground. So they are beaming all to the same tower, and then the energy is used for heating. Now, this is one illustration, and it was actually a successful pilot. But even for this shallow reservoir, so a depth of, I think, 250 to 500 meters, there were quite a bit of losses of energy. So downhole electromagnetic heating could be a solution to reduce those losses and then make the project more viable. Another example that I have, which is shown here, is the actual use of electromagnetic heating for environmental engineering application. In this specific case, instead of excavating the soil and treating it with thermally to remove the contaminants and the pollutants, what we do is that we inject energy, and then this energy will lead to, similarly to the crude oil that I just mentioned, will mobilize the pollutants, so the dense non-aqueous pollutants, and will also vaporize the light non-aqueous pollutants. Those are the vaporized ones can be extracted in different ways, but the dense ones can be extracted as fluids using the wells that are here. So the main feature I would like to stress here is that you have here an element which will hit the reservoir, so electromagnetically hit the reservoir, and then so next. Now, these two examples have brought us to the following problem: the problem of heating and two-phase flow in the subsurface, which we decided then to treat the way we do at the universities, by combining controlled experiments and modeling. So I will start to explain the main features of the modeling approach. Now, first we consider an homogeneous anisotropic medium, and for simplifying things, we consider a cylindrical porous medium with cross-sectional area A, and then we suppose, we assume that the medium is at a certain saturation state, characterized by SWI and SOIL I. S-oil could be oil, but it's just the non-aqueous phase. And then in this medium, what we will do is that we will inject water at a certain flow rate, Q, and then we will have a device which will heat up the system. So we will use a microwave source. The frequency is tuned to 2.45 gigahertz. These are the microwaves that everybody finds in his or her home. Yeah. Now, to solve this problem, we of course will formulate the corresponding governing equations first, and do not pay attention too much to the equation. I just want to convey a few ideas here. So the basic thing is that by using this device, an electromagnetic means of heating the subsurface, we are going to create a certain electric and magnetic field. The electric field will excite water molecules, will induce a rotation into the water molecules so that energy is dissipated into heat. Now, this heat will be, so the water will be heated, the temperature will increase, and that increase in temperature will lead to the decrease in viscosity of all fluid phases in present. All right, so that's what's indicated here. We have an equation here which describes energy conservation, in which you have the heating up over here that leads to decrease in viscosity. Part of the heat is going to be absorbed also by the rock, which actually is we found out recently that it's in fact a serious complication, because the rock represents often up to 80% of the total volume. Now, in this picture, I would like to make one remark. So this would be a 2D projection of the heating up of the core. I just want to zoom in a little bit into the pores to make the following remark. So, as I said before, we have this material, which consists of the rock fabric, the fluids, so the water phase, which is in this case is wetting completely the rock, and the non-wetting phase. And now the water will be heated up, and then the heat transfer to the other phases, so to the oil and to the rock, will be mainly by diffusion, okay, by thermal diffusion or conduction. Now, the equations I showed you in the previous slide assume that the thermal diffusion is instantaneous. Yeah, so that's the problem I was mentioning, that in fact that assumption may not be sufficient. So the equation would have to be written in a different way. So now, next, as I mentioned, we decided to do experiments. In order to do these experiments, we designed and constructed a dedicated setup that you can see here. I'm just going to point out the main elements of the setup. So in the center, you have the test section or the core holder, in which we place a porous medium, for example, bentime or sandstone. And then the EM generator is, of course, outside here. And we found a way to inject the fluids just immediately after the EM generator. Now, the EM generator is connected to the core through an aluminum tube with holes, and this aluminum tube serves as a waveguide. And then, now, yeah, we want to measure temperatures, of course, and we cannot use classical thermocouples. So what we decided to use are a fiber optic temperature sensors, which are almost not affected by the electromagnetic field. Now, here are some results that we obtained. So in order to calibrate the setup, we decided to just heat up the core sample without any flow in the system. And then we estimate, we measure actually how the temperature is increasing as a function of time. So we can calculate the rate of increase of temperature as a function of distance in the core. Well, this was a kind of low budget experiment. So we had only 4 temperature sensors, but okay, we can see the trend quite clearly. And then after obtaining the temperature profiles, we can, of course, derive the power that is absorbed by the water. And well, you have to take my word for this, but these lines, they follow a very nice exponential form that is given here. So this exponential form was actually unknown at that time, and we will see later on that without giving details, that actually we can derive it from first principles by just solving Maxwell equations for the propagation of the electromagnetic wave in the porous medium. Now, the next step, of course, is to check whether our ideas were correct or not. So we decided to compare the experiments with the model. And in order to do that, we relied on an analytical solution, which was obtained by the method of Duhamel. The idea came from Grigory Shapiro from UFJF. And well, the details are given in the reference here. But so essentially, well, we can immediately see that it's not an exact match of the experiments with the temperature. That's not very surprising, because in order to apply this Duhamel-Shapiro analytical solution, we needed to completely decouple the flow from the heat equation. So we introduced a quite crude approximation. That's one point. The second point is that we needed also to, we didn't have a way to estimate the heat losses, which we found out later on that were kind of important, very important. Now, with this, we have asked ourselves the question: could we use EM heating of the subsurface to store energy and therefore to solve the problem of intermittence of solar and wind power? I'm not going to discuss that. I assume that in the audience, everybody is absolutely familiar with the fact that these two sources of renewable energy, they suffer from this problem. And then from a more general point of view, actually, we can ask ourselves, if we have an EM source which is not emitting at a certain constant rate, but has a certain variability, what is the impact on the injection of energy into the subsurface? And to answer this problem, we decided to look at a higher scale, at a larger scale than what was done for the previous cases. So we considered the following problem. We consider a reservoir, an aquifer, with the following dimensions: 100 by 100 by 2 meters, into which we inject water at 40 microns per second. And yeah, you can convert this to typical velocities that are used to inject fluids into reservoirs, either geothermal or oil reservoirs. And then we chose a well configuration, which is called in the jargon of GeoEnergy, the 5-spot configurations, where we have one central injector and 4 producers. And then we looked at continuous injection, of course, as a first test case. And then we looked also into the alternating injection. So we inject water and energy for a period of 6 months. And then also we look at the production of the water in the consecutive 6 months. And we do that for a period of 6 years. Yeah. So these are the results that we are going to discuss. And so for every injection is done, injecting water together with an active EM heating. Now, this problem is slightly different than the previous one. I would say slightly simpler than the previous one, because we don't have two-phase flow, we have single-phase flow. And then we can formulate the equations a little bit differently. In this specific case, we can assume a radial symmetry, and therefore, for that case, the expression for the source term, for the heating term, is given simply by this decaying exponential with the radius. Yeah, avoid the singularity is not a problem because we start at the radius of the well. This is a paper in preparation by Almeida et al. And then we included the loss terms, which I will discuss in more detail later on. It's important to note that here we completely couple the flow with the heat equation, with the mass balance. Yeah. So because we are interested in a large-scale problem, we cannot do experiment. At least it would be much more difficult to do experiment. We decided to solve this problem numerically, and this is one set of results. So I will slow down a little bit here to explain. 3D pictures are always more difficult to. So what we have here is the temperature. Here we have the distance towards one side of the domain, and this is the distance toward the other side. So this is the central well, and over here we would have one of the producers. And one interesting thing that we see immediately is that the water is injected at 35 degrees, so it's heated up from the inlet up to a certain point into the reservoir, and then the temperature drops as you go far away. This is the situation. It's a snapshot after 6 months, during the storage cycle. And then in the next 6 months, we are going to extract the hot water. And now, yeah, this is the situation after the extraction of the hot water. We don't go completely back to 35 degrees near the well. And so what we see is that, well, the temperature has decreased as should be expected. And then here what I show is the situation after cycling 6 times. So we do this for 6 years again. So this is the last storage cycle, which is by all means similar to the first one, and this is the life cycle. And so we can see the aquifer as a reservoir where we can store heat and extract, store and extract. Yeah. And then there is something that we need to examine a little bit more closely, and that is the heat losses. And so in this graph, which are profiles, are giving profiles, temperature profiles for the diagonal between the injector and one of the producers, or at least between the central well and one of the edge wells. And then now here you see the storage over a period of 6 months, and we see how the temperature actually evolves. And the interesting thing is that we have 3 sets of data for CL. CL is the coefficient that describes the heat losses. So we increase it, and what we see is that at least within this range of values, there is very little effect of the CL coefficient on the storage. But for the recovery cycle, we see a more significant effect, but also not shocking. Now you could say, well, in fact, this CL is totally arbitrary. So probably if we take much larger values, we will have a completely different result. I will say that's okay, but we don't have a real proof for that until we do experiments at this scale. Now, and then what we can do, we can take the data, and now here we have the energy that has been. So this is the energy that has been injected into the reservoir, and this is the energy that we recover for different values of this loss coefficient. And now clearly for the lowest loss coefficient, even for the lowest loss coefficient, some energy remains in the reservoir, but almost 80% of the energy is recovered. So it is a real, let's say, storage, temporary storage, but in a nice sense of the term, because it means that we can use it to store and take out the energy. The question that then I have, maybe as a discussion, to which extent we could use this in combination with the most well accepted concept for geothermal energy exploitation. And yeah, before I continue with that, I just want to mention that this cartoon here was made by Shapiro, who is a mathematician, so that is remarkable that he could make such a nice drawing. But coming to the question I just asked, this is a typical geothermal system, and then I just want to draw your attention to the fact that we re-inject the water here at 25-30 degrees Celsius. Yeah, so it seems very appealing to combine the analysis that I just made with this injected water, so that we equip this injection well with a heating, with a downhole heating element, electromagnetic heating element, in order to ensure that the temperature of the reservoir is not dropping too much, and then we could increase the longevity of the life cycle of the geothermal system. This is just an example, so there are many other cases in which I believe we can use this method to improve the efficiency of geothermal systems, but it's also not a panacea. So it is very well possible that for the systems, especially the shallower ones, the method will not work. And so I just want to go to a few points, a few takeaway points. The first one is that now from our observations in the lab, from the modeling, if we combine the two, it seems that downhole EM heating is a highly efficient method for injecting energy into the subsurface. well, that regardless of whether it is useful or not. This method can potentially help address the intermittency of solar and wind and wind power. I'm absolutely convinced of that. But more work would be needed to quantify more accurately the heat losses, and I think the work would be on the appropriate scale, so on a reservoir scale rather than only on the lab scale. And then what we put it completely under the carpet are geochemical effects, because if you are going to heat up rocks, a lot of effects will exist between, a lot of interactions will exist between the fluids and the rock, which will have impact on the working of the whole system. And finally, again, so for probably this method of heating the subsurface will help a certain geothermal system, but not other ones. So studies have to be done on a case by case to check whether both in terms of efficiency and also in terms of economics, the method will work. This is what I wanted to tell you this afternoon, and I would be happy to entertain any questions.
Thank you, Pacelli, for this very interesting talk. I really enjoyed listening to that and learned a lot. Sebastian will take over the question and answer session. I also would have a question.
Yeah, then go ahead, Maren, please.
Okay. Pacelli, that's an interesting approach you present, and I think also very new and still has to be studied. I wonder, what would you need from the geothermal operators, or probably also geothermal researchers, as information to make your system more reliable or stable to set it up?
So what we would need are cases, so with a complete reservoir description, data about thermal properties of the fluids, of the reservoir itself. But I believe in actually testing this in the field. So what I would be happy to have is a case, a reservoir case, where we can go and test it in the field. It can be just an estimate. It can be relatively low cost to do a field experiment where we test the whole concept.
Do you have a kind of wish list where you would like to try that?
So my first wish list, actually, I have it for some time already, is some shallow aquifers that one finds in Suriname, which belong to the Suriname oil company. And these aquifers, of course, they also have oil reservoirs, but these are aquifers which are fairly well characterized with plenty of wells. Other possibility are, for example, in the Netherlands, some shallow aquifers, maybe A-test systems. I don't think that in terms of efficiency, A-test systems are the best ones, but for the proof of concept, to use that word, it would be excellent to have one to just test the whole lot.
Yeah. To also try, yeah. Thank you. Then I first give back to Sebastian.
Yeah. Thank you. So yeah, we have some questions from the audience. The first one is from Mosen. Thank you for the presentation. What are the practical actions or conditions to prevent heat losses in real field applications?
Okay. Hi, Mosen. So heat losses, we cannot prevent them, probably, in the field, at least in the reservoir. We can prevent heat losses in the well itself. We can reduce them as much. And the fact that we inject the energy downhole is one of the ways to prevent those heat losses in the well. Yeah, but it is inherent in the system. We just have to understand them. Yeah.
We have two questions that are very similar to each other. So we start with the one from Bill Rossen, and then we go, and then I follow up with the one from Florian. So Bill asks, really interesting talk. Using electromagnetic heating is more efficient than using electricity for resistance heating. How much energy is lost turning electricity into electromagnetic radiation? And Florian asked sort of a very similar question. Thank you for the presentation. From a basic physics perspective, surprised at converting electric energy into heat and to convert it back into electric. Wouldn't an alternative, for example, compressed air, hydrogen, methane, etc., be more efficient? So how efficient, do you have any feeling of how efficient the energy conversion process is?
The conversion of electricity into EM and then the heating is very efficient. I think one can reach efficiencies in excess of 80%, depending on the design of the microwave device. Yeah, so that's and it is. So what we are trying to compare here is heating the water at the surface versus heating the water downhole. Yeah, if we compare these two situations, still heating downhole using this EM will be a winner. That's one thing. To compare this to compressed air, to hydrogen, and it's a work that we did not do. It is possible that doing electrolysis and to make hydrogen and then burning hydrogen to produce heat and etc. I expect more losses there, but the quick answer is that we didn't do this comparison, so I cannot say which one is more efficient. Maybe it's a suggestion for people listening to do this work.
There's certainly an interesting aspect related to the efficiency, but also how easy it is to actually manage the reservoir. Heating and cooling the reservoir is probably less risky in terms of constantly increasing, decreasing the pressure if you were to store methane or hydrogen, leakage risks, etc. So there could be a really interesting trade-off to consider in terms of the efficiency versus risk and versus the overall economics. Before I take Christine's question, then I have sort of a follow-up question myself. Christine asks, with the high temperature of injected water, how much uncertainty is introduced into the flow behavior of the heated fluid? So in terms of geologic heterogeneity or possible background groundwater flow.
Oh yeah, this is an absolutely interesting question. So actually, in everything that we did, and we assume everything to be nicely homogeneous and isotropic. And my colleagues who are geologists were probably not around because they would have summoned me to take into account the correct geology. I think, so first of all, the thermal properties of the reservoir will depend on the fabric of the rock. So that will be one source of uncertainty. The uncertainty in the heat transfer between the water, the injected water, and the rock itself, but also on the flow paths. So the flow of the fluids will also be affected and that's why I mentioned in one of the conclusions that actually in order to determine the feasibility of this approach, one has to look at at each case. On a case by case, one can determine whether it is feasible or
not. Thank you very much for this. We have another question from Ahmad, thanking you as well for the outstanding presentation. His question, the question is, have you come up with a criteria list of reservoirs? Which one would be the first reservoir that you would target? We talked a little bit about, Maren asked you sort of what we need in terms of the geothermal side. You had some ideas, but what would be sort of optimal reservoirs that you would like to target first?
Yes. In order to test this method, I would start really with a simple, let's say, kind of sedimentary type of formation, not too deep, not too shallow, because if it is too shallow, then there is no merit in the method. So kind of very simple, just to prove that it actually works the way we think it works. And after that, I mean, once the method has been proven, we can adapt it at will to other sorts, to other types of reservoirs.
So I was thinking back to last week's talk, and so as a follow-up question to what Hamad asked. So last week we had Thomas Kohl talking about the deep store project that they're doing in Karlsruhe on campus. So how easy would it be to have a little pilot test site, say, on the TU Delft campus? And I thought TU Delft does have at least discussion about a geothermal borehole.
Correct.
TU Delft. So how easy would it be to do something like in Karlsruhe on campus to learn, generate data?
Just on top of my head. So if you have a well which is completed with an injection tubing and etc., you have to pull the whole lot out and then place your EM. So you have to design it specially for that. So it's engineering wise. I would say it is feasible. It's also not, there are no complexities that we cannot solve, but it is something that will incur some cost and will cost some effort. But it should be feasible. I mean, it should not be too complex. The challenge there is that if the reservoir is too deep, because the idea would be to place the EM heating into the well and then measure the temperature out at several distance away from the well, like in one of the schematics that I've shown in the beginning. And if we have a very deep formation, that means that we have to drill additional wells where we are going to measure the temperature, and that's just too costly. Even for funding agencies, research funding agencies.
Yeah, I'm thinking there's a lot of sort of nice open space around the Heriot-Watt University campus. I'm just already planning, thinking of how we could put some wells there and perhaps do a little bit of tests, very shallow, but at least sort of understand some of the system behavior. We do have two questions coming in around temperatures. And so the first one is sort of a question around one of your slides. So Raymond wonders, on one of the slides you had 365 degrees centigrade on the scale. Is that correct?
Let me just go back to 365. Yes, that is correct. That is correct. That is correct, and it's extremely high temperatures. I didn't mention it, but we constrained the model with extremely high pressures as well, 20 megapascals, to ensure that the water is not going to that we don't have vapor phase. But when we started this part of the study, the last part of the study, we were thinking of deep geothermal wells let's say up to 2,000 meters, where the temperature is around 80, 90 degrees Celsius, maybe going to 100. So, and the water is injected from some surface, so it's still cold water, at least much colder than the reservoir.
So, in following up on this temperature question, you probably have answered it to a large degree. Jingwang, hello, Dr. Zitha, nice talk, thank you. How deep do you estimate that EM can heat the reservoirs to, for example, 500 degrees centigrade? Distance depends on the porous media, but is there a general estimation? So what are the maximum temperatures that you could reach? Not that you want to reach them, and how far could the temperature penetrate into the formation? The temperature normally.
How far the temperature can? Yes. Okay. So now, yeah, what the studies that we have done with these 100 meters have indicated is that we could make this temperature go up to about say 15 meters in 6 months. And that has to do with radial geometry, right? That the front actually slows down as we inject. So if you want to inject, I don't know, either with much higher power, because there is no limit to. I mean, if you wanted, you could just heat up to the reservoir to whatever you can. Calcinate everything that is possible to calcinate. But so if you inject long time enough, you could penetrate, I would say, an arbitrary distance, but then you have to wait or you have to inject for a long time. And the volumes injected will be huge as well, also on account of the radial geometry.
Thank you. We do have another question here. From Wesam, again, thanking you for the presentation. If there are some minerals in the subsurface that have ferromagnetic effects, iron-rich, iron oxides, pyrites, etc., would there be any problem for electromagnetic heating?
The short answer is yes. So, if you have ferromagnetic materials in the system, they will interact with the magnetic fields. But what the effect would exactly be, I don't know. From experience, I know that from domestic ovens, from that you can create what we call hotspots. So these are places where the temperature, or at least the absorption of the energy will be non-linear. So you get a huge increase in temperature, and that is what we. So if you misheat your bread, for example, you will have black spots at some places, and that's what happens. That you have these hot spots.
I should point out that Bill Rossen and again Qingwang had very similar questions around the effect of
minerals,
any type of iron material, iron minerals on heating. Perhaps this is more a comment than a question. So Raymond came back and said, in the shallow Dutch subsurface, current regulations do not allow to go above 25 degrees centigrade. So all high temperature aquifer thermal energy storage needs to be treated as pilot. So I guess it's more a comment rather than a question. But is there anything you would like to add to this, Pacelli?
Oh no, I think Remo is absolutely right. So. With the present set of simulator, we wouldn't be allowed to touch the Dutch subsurface, and that quite rightly so. I think the water table is very high, and then you would create a kind of mess by making such high temperatures. That's absolutely right.
Okay, I think then no further questions coming through. So thank you very much, Pacelli, for answering all the questions. Thank you to our audience for posing these insightful and interesting questions. And Maren, back over to you for some final comments.
Yeah, thank you, Pacelli, again. It was really inspiring, I think. So yeah, finally we are pleased to announce the speaker of next week, which is Joya Falcon from University of Glasgow. And she will speak about, she gave the title From Subsurface Characterization to Resource Assessment, Inherent Risk and Uncertainties. So we are very much looking forward to welcoming her next week. And also you, we hope to see you again. Have a nice afternoon.
Thank you.
Thank you very much. Thank you, Pacelli. Thank you to our audience. Thank you, Maren. And see you all next week then.